This is the start to Chapter 3, where we're looking at the intersection of lines and solving systems of equations. So starting with Lesson 3.1, we're going to look at the basic overview, which is solving a system of equations by graphing, which is really just looking for if two lines intersect, and if so, where. First thing we're going to look at is this problem. You're going to see problems like this throughout the chapter, but we're going to do different things with them in different sections. So, first one, we have an equation that says 2x plus y equals 5, and then x minus y equals 1. Each of these are lines. The easiest way to see that is to rewrite them in slope-intercept form, the y equals mx plus b form. So if we take this one here, and you were to subtract 2x from both sides, you would get it to look like this, y equals negative 2x plus 5. And if you were to graph that, y equals negative 2x plus 5, you would start at 5, and you would use a slope of negative 2, which is a steep downward slope, and you would get this line right here. On the other side, we have this x minus y equals negative 1. If you add y to both sides and subtract 1 from both sides, you're going to end up getting this line right here. So y equals x minus 1. And if we graph that, we're going to start at 1 as our y-intercept, and then we're going to go up 1 over 1, because we have a slope of 1 over 1 here. And so those are our two lines. And now the whole goal of this is to figure out where these two lines intersect. That is our mission here. So it looks like they intersect at this point, which is the point 2, 1, over 2, up 1. So the answer to the solving this system of equations here would just be a single point. So you'll find that these problems, instead of having lots of short problems, you're going to find that you'll have very few longer problems. Solve this system of equations, you do a bunch of work, and you're going to get this point. One of the nice things about this chapter is that whenever you get an answer, you can plug in your value of x back into the x of each equation, and you can plug in your value of y into the y of each equation, and you can actually check your answer. So I'm just going to do that very quickly here. 2x plus y equals 5. Well, if x is 2, and then we have 2 times 2 plus y, which is 1, equals 5. And yes, 2 times 2 equals 4 plus 1 equals 5. So that one works. And then the other one, x minus y equals 1. If x is 2 and y is 1, so 2 minus 1 equals 1. Yes, well, that is definitely true. That checks out. So this solution does in fact work. So that's always a good way to make sure you did the right thing. Moving on, we have some terminology for different situations. Sometimes we're going to have situations like the last one where we have two lines that intersect at a single point. That means that they are consistent and independent. The way I like to remember this is that consistent starts with a C, and so does cross. So when two lines cross, they are consistent. Now, you'll notice that this one here just says one line, and this one is also consistent. So clearly there's really nothing crossing. So why would I choose that as a way to remember it? The reason I did is because these two lines here are on top of each other. You only see one because there are two lines drawn directly on top of each other. They're the same line. So they cross at every single point. They're always touching. They're always intersecting. So whether they cross at a single point or they cross at every point, we're going to say that they are consistent. Now, consistent is cross. Consistent means they are intersecting. The difference here is that this one is independent and this one is dependent. Now, if you think of two people that are independent of each other, they don't necessarily rely on each other. They don't need each other all the time. Same thing with these two lines. They only intersect once. They don't need each other all the time. They're very independent. These two lines here are very needy. They need each other all the time. They are depending on each other. And so that's how I like to remember that two lines that always intersect are consistent, they're always crossing, but they are dependent on each other, whereas these are independent. Now, if they never cross at all, if they're parallel lines, they will never, ever, ever cross. They are just inconsistent. So consistent means cross, inconsistent means don't cross. Taking a look at the next example here, it says graph the system and describe it as consistent and independent, consistent and dependent, or inconsistent. Well, if you take these two equations over here and you convert them into their slope-intercept form, we're not going to look at the algebra part right now, but let's say you convert these two lines here into slope-intercept form so they're easy to graph, and then you put them on your graph. We're going to have a y-intercept of 10, which is probably way up here somewhere, and a slope of -2, so over 1, down 2, over 1, down 2, and we pick up right about here. Same idea here, we have a 2/3 slope starting at 2, so we start at 2, and we go gradually up, so over 3, up 2, and we graph this line. And it looks like they intersect at a single point. So when they cross, they're consistent. Because they only cross once, they're independent. So consistent and independent. Now let's look at an example where they're the same line. You would think that you'd be able to detect that two things are the same line very easily, but in many cases they're written like these two equations up here. 9x minus 6y equals 24, 6x minus 4y equals 16. Until you start to solve them and get them into y equals mx plus b form, you're not going to always notice that two lines are the same line. One thing that you might pick up on is if you multiply every one of these numbers by 1.5, you will get the other equation. But if you don't notice that, the best way is to just start putting it into that y equals mx plus b form so it's easy to graph. And when you do that, if they're the same, you will notice it right then every time. So no matter which one of these you pick, if you were to graph it, it's going to just be this line right here. So how many solutions are there to this equation? There's infinity, because where do they cross? At infinity points. And how would you describe it? Well, they are crossing each other, so we'd say consistent, and they are very needy. They cross all the time, so they are depending on each other. They are dependent. Next example, looking at parallel lines. Same idea as the last problem, where we took our two equations up here and we converted them into the y equals mx plus b form, because that allows us to notice things such as the fact that they both have the exact same slope. So these two lines over here have exactly the same slope of -3/4. And when you notice that two lines have the same slope, it means they're going to be parallel, unless they're the same line, in which case the whole thing would be the same. But over here, the y-intercepts are different. So we'll have one starting here, one starting up here, but they both have exactly the same slope. When that happens, those lines will never touch. Parallel lines go on for infinity in both directions and never touch. So that's why it is not consistent, it is inconsistent. And then finally, last example is looking at a word problem. And this is something that comes up in economics quite a bit. There are two equations that are being built from this situation. Travis and his band are planning to record their first CD. The initial startup cost is $1,500 and each CD costs $4 to produce. They plan to sell their CDs for $10 each. So on any given CD, they're making a profit. However, they have to sell quite a few CDs before they can make back that $1,500 startup cost. So they want to know how many it's going to take before they make a profit. And again, in economics, you're going to see two curves. You're going to see the money coming in, which is what I'm highlighting right now, the income, which starts at 0 and works its way up, and then your cost, how much you have to spend. And that's usually going to start at some starting point and then go up a little bit more gradually. The idea is that if you sell lots, you're going to make money, but if you don't sell very many, you're probably going to lose money. So the break-even point is where those two lines cross each other. The way that you set up these equations is your y is typically going to be the amount of money you're making. So you'll start that over on one side, the amount of money you make. And the slope the number that goes next to X is going to be the amount of money you make per item. So per CD. If you're selling CDs for $10 each, or it's going to cost $4 for each CD to produce, those are going to be the slopes. The reason is because X is your number of items, your number of CDs. So as you produce more CDs, you want that cost factor to go up. So that's why it's the slope. The thing on the end here, the startup cost, is something that you have when you first start producing the CDs. Even when you've made no CDs yet, you've had to spend money to get started. So that's going to be your y-intercept. Usually when you're selling things down here, you're going to have a y-intercept of 0 because it doesn't cost anything to necessarily start selling, to start making money. But it does cost money to start producing your items always. So that's the basic idea of this one. And once you have come up with these equations, you've graphed these lines, the way that you would actually answer the question would be to look at where is this intersection point up here. And it looks like this intersection point happens at 250 CDs and $2,500. So their question, how many CDs must the band sell before they can make a profit, would just be right here, 250 CDs. And that's it for 3.1.